Hello everyone. Until the last lecture, we have covered Rosenberg perceptron concept. In the present scenario, in the present lecture, we will going to discuss the perceptron convergence theorem. In the last module, we have discussed concept of perceptron. So before starting the concept of perceptron convergence algorithm, let me draw a signal flow graph of the equivalent signal flow graph of the perceptron, and the dependence on the bias dependent on time has been omitted for clarity, and for a clarity purpose, dependence on time has been neglected. Okay, so starting with this concept, let me share my screen. Start. Okay. So as I've discussed, I'm going to start with a equivalent signal flow graph of the perceptron, which is like this. Now this is my inputs IP, and this is my fixed input of x naught equal to +1 and +1, and corresponding weight vector W naught is equals to V, and this is my V input V. Then we are passing this to a hard function defined by this is also called a hard limiter. And we have a corresponding output. Okay, and this is my x1 input, x2 input, and corresponding to xn input, and the corresponding weight associated with it is given by W1, W1, W2, and Wn. So this is my equivalent signal flow graph of the perceptron, and dependence on time has been omitted for clarity. We'll consider this signal flow graph for our perceptron convergence theorem. Okay, for consider this for perceptron or concerted convergence theorem for proof of perceptron convergence theorem. Okay. So moving on to further, in the model we have considered in the figure, the bias Bn is treated as a synaptic weight driven by a fixed input equal to 1. That is, we are considering the bias term that we discussed as bias term as which is equals to, which will be omega naught, that is which is equal to, which is described as a fixed input, that is +1. So we can define it in +1 input vector. So m +1 by 1 input vector as xn +1 x1n comma x2n comma up to xn. M in transpose, where this N denotes the time step in applying the algorithm. Okay, and correspondingly we define the correspondingly, this is for the input vector. We're defining the input vector as x1 plus 1 x1 and x1 n x2 n dot 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 up to xm n transpose, and where the n, where this n is the time step in applying the algorithm. And similarly we will define the weight vector w n is equals to the bias term comma input vector w1n w2n up to wm trans n transpose. Okay, so using the linear combiner, using this is the equation number 2, and where x, when we are defining x, when we are defining x n is 1 x1 n comma x2 n to xm n transpose. This is my equation number 1. Using using the linear combiner, the linear combiner output can be written as Vn is equals to summation of I equals to 0 to n, so to m w1n x win xi of n, where I is in the range of 0 to m, which can also be written in the form w transpose n xn. Okay, so this is my question 3. The first assumption for the first start for the learning of perceptron convergence theorem, we will consider a EC equivalent signal flow graph that we have discussed a few minutes back, and we present that corresponding input vector as xn and corresponding weight vector at wn, which is represented in equation 1 and 2 respectively. Equation 1 and 2 respectively, and the linear combiner can be output can be written in the form Vn w1n x1n. For the first line, now the first line of the first line w0n, that is in the first line, if we have, when we are defining this this e Vn is equals to summation of I is equal to 0 to m wi n and xi n. So the first line of this equation to corresponding, that is I is equal to 0 term, represents the, when I is equal to 0, it represents the bias term. For fixed n equation, w transpose x is equal to 0, that is for fixed n, the equation can be written as w transpose x is equal to 0, and plotted, can be plotted in and be plotted in an m dimensional space. In m dimensional space. Okay, and for spacecraft, some spacecraft bias with coordinate x1, x2, xn defines a hyperplane where x1, x2, dot 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 up to xn defines a hyperplane. Okay, hyperplane as a decision surface, as a decision surface between decision surface between two classes of classes, between two classes. Okay, of input. Let me just this. For the perceptor to function properly, the two classes, let us define two classes as C1 and C2. Between maybe is linearly separate. It is linearly separable. Okay. Now something like this. Suppose I have a class of C1, and this is a decision boundary. This is the decision boundary, and this is my C2. Okay. And this is for linearly separable patterns. Okay. Okay. This means that the patterns to be classified must be sufficiently separable from each other to ensure the decision surface consists of a hyperplane. Okay, this is restricted. Okay, for the two-dimensional, this is for two-dimensional 2D perceptron. For a 2D perceptron. Okay. Now, when it is insufficiently separated from each other, when the two classes are easily separated for each other, for us to draw a hyperplane as decision boundary. If, however, the two classes C1 and C2 are allowed to move too close to each other, they become non-linearly separable, a situation that is beyond the computing capability of the perceptron. So here lies the limitation. What is the limitations of the perceptron? When two classes are very close nearby to each other, suppose like this, we cannot put a decision boundary. We cannot put a decision boundary over here. Okay, C1 and C2, and in this case, perceptron theory is limited. Okay, so for the perceptron convergence theorem, first thing we have to consider that two classes are linearly separable in a limited separable pattern. Okay, suppose then the input of the variable of the perceptron originate from the two linearly separable classes, and H1 be the subspace of the training vector. Let us consider of the training vector. Let us consider two types of vectors. One of our training vector, which is one like this x1, which can be defined as H training vector can be defined as H1 for class 1, and which is with corresponding input vectors are x11, x2, x12, x12, x3, sorry, x13, like this, up to x1n. And what this is for class C1. Then H denotes training vector. Okay, and for class C2, we have H2 is equal to x21, x22, x23 up to x2n. Okay, now clear? The union and a union of H1 and H2 is complete space is denoted by H1 when H is denoted by union space. It is if we denote the complete training vector as H as H1 union of H2. Okay, given sets of vector H1 to train and H2 to train the classifier, training process involves adjustment of weight vector in such a way that two classes are linearly separable, that there exists a weight vector in such a way that we may state x1 transpose, that is, then we can say that x1 transpose of x is greater than 0 for every vector belongs to a vector of class x belongs to class C1, and W transpose, I have made a mistake, W transpose x is greater than 0 for all the training vector x belong to class C1, or W transpose x less than equal to 0 for all the vector input vector x belong to class C2. This is the condition. And in the second line, we have arbitrarily chosen to say that input vector x belong to class 2 if a W transpose x is equal to 0. Now, given the subset of training vector H1 and H2, the training problem for the perceptron is then to find the weight of vector W such that two inequalities of these two inequalities are satisfied. Now, the algorithm for adapting weight of the elementary perceptron may be now as formulated as: number one, if the nth member of the training set xn is correctly classified by the weight vector computed at the nth iteration of the computed at nth iteration of the algorithm, then the weight vector of the perceptrons in accordance with the rule that we have discussed few minutes back can be written as W of n plus 1 vector is equal to Wn if W transpose x is greater than 0 and xn, the input vectors belong to class C1, and vice versa, Wn plus 1 is equals to Wn if W transpose x is less than equal to 0 and xn belongs to class C2. Okay, this is the first rule, first algorithm of the adapting weight vector of an elementary perceptron. Okay, now the second can be stated as otherwise the weight vector of the perceptron is updated in accordance with the rule, then W of n plus 1 is equals to Wn minus neta n xn if W transpose n xn is greater than 0 and belongs to class C1. Similarly, Wn plus 1 will be Wn minus neta n xn, that is W transpose n xn is less than equal to 0 and belongs to class 2, where neta n is our learning parameter. Okay, that controls the adjustment applied to the weight vector at nth iteration. Now, if neta n is equal to neta greater than 0, where neta is constant independent of the iteration number n, then we have a fixed increment adaptation rule for the perceptron. If this condition holds, then we can call this as a fixed increment, adaptation rule for the perceptron. Okay, for the perceptron. In a sequel, we first prove the convergence of the fixed incremental adaptation rule, for which neta is equal to 1, and clearly the value of unimportant so long is it positive. A value neta is not equal to 1 merely scales the parameter of a pattern vector without affecting their separability. The case of the variable neta n will be considered later. Now, proof of the perceptron convergence algorithm can be stated here. For the initial condition with W 0 is equal to 0, and suppose that W transpose n and xn is less than 0 for n is equal to 1, 2, 3 up to n, and the input vector xn belongs to subclass of xn input vector belongs to subset of the class h1n. Okay, or h1. Okay, and that is the perceptron incorrectly classifies the vector x1 and x2, and since the second condition of the previous equation is violated, then with the constant neta is equal to n is equal to 1, we may use the second line to write a wn plus 1 is equal to wn plus xn for x1. Xn belongs to class C1, and given initial condition, that is given initial condition of this W is equal to 0, we may iteratively solve this equation for Wn plus 1 term, then which can be written as Wn plus 1 is equal to x1 plus x2 plus up to xn. Okay, since the classes and C1 and C2 are assumed to be linearly separable, there exists a solution W0 for which W transpose xn is greater than 0 for the vector and belonging to subset of h1. For a fixed solution W0, we may define a positive number alpha, such as we can define alpha for if we are considering the fixed set of fixed solution for W1, we are considering fixed solution for W0 case, then we define a number alpha in such a way that is equal to minimum of xn, which belongs to h1 class, h1 subset of the training Wn plus 1, it is of x1 plus x2 plus up to xn. If we multiply this two equation on both sides, we will have the equation of the form W naught transpose Wn plus 1, which is equivalent to W naught transpose x1 plus W naught transpose x2 plus W naught transpose xn. Okay, and according to the light of the definition, this W naught transpose omega n plus 1 should be greater than equal to n into alpha. Okay, and next we make the use of an inequality, not Cauchy-Schwarz inequality, and given two vectors W0 and W1, if you use the Cauchy-Schwarz inequality, if you use Cauchy-Schwarz inequality, inequality, we can write the previous equation of W transpose, that is W naught transpose W plus W of n plus 1 greater than equal to n alpha. If you use the Cauchy-Schwarz inequality, then we can write this equation in the form as W naught square mod of W n plus 1 square to be greater than equal to W naught transpose W n plus 1 square. Okay, and this double modulation denotes the Euclidean norm of the enclosed uncomment vector, and the inner product, that is W omega W transpose W naught transpose W n plus 1 is a scalar quantity, and this is a scalar quantity. Now, from this equation of previous equation, we can note that that W naught transpose W n plus 1 square is equal or greater than n square plus n square alpha square, and this is n square greater than n square alpha square, and we note that W naught transpose mod of W naught transpose square W n plus 1 square is equal to or greater than W transpose n plus 1, and we follow, therefore can be written, and this can be further written as should be greater than equal to n square alpha square. We are just continuing this equation, for which can be equivalently can be written as mod of W n plus 1 square, which is greater than equal to n square alpha square divided by W naught square. Okay. Now next we follow another development route. If you consider another development route, we will do the similar thing and rewrite the previous equation in the form that is W k plus 1. And it's another way of proving this. So this is equal to, can be written as W k plus x k for k equal to 1 to n. Okay, and x k belongs to training set h. And by the squared Euclidean norm of the both side, if you perform the squared Euclidean norm, which can be written as W k plus 1 squared is equal to mod of W k square plus mod of x k square plus twice of W transpose k. This is nothing but squaring both sides x. Okay, but we know that W transpose k and x k is less than equal to 0. Therefore, we can deduce the previous equation can be equivalently as this equation. We can deduce equivalently as, we know that W transpose k x k is less than equal to 0. Therefore, this previous equation that we have deduced, we can write that equation in this form: W n plus 1 mod square is less than equal to mod of W k square plus mod of x k square. Okay, or which can be equivalently written as mod of W n plus 1 square minus mod of W k square, which is less than equal to mod of x k square, where k is equal to 1 to n. Adding these inequalities for k is equal to 1 to n, invoking the assumed initial condition for, if we assume the above initial condition, that is what is your consider w0 is equal to 0, we get an inequality of the form mod of wn plus 1 square, which is less than equal to summation of k is equal to 1 to n mod of xk square. Okay, and which is also can be written as less than equal to beta n into beta, and beta can be defined when beta is a positive number, and it's nothing but beta is nothing but the maximum value of xk, which belongs to training vector h1 of mod of xk square. Okay, okay, clear up to now? Or this previous equation states that squared Euclidean norm of the weight vector grows at most linearly with the number of iteration. That this continuously goes on with iteration, it goes on completely linear. Now, second result of this previously equation, that is of this equation is clearly in conflict with the earlier result of previous equation of this form of the Schwarz inequality we had. In the Schwarz inequality part we had, it's for sufficiently large value of n, and we can state that n cannot be larger than some value of n max, for which equation of this and this equation 16 and this equation and the previous equation of that we used using Schwarz inequality are both satisfied with equality sign. And that is and that n max is the solution of the equation of the given form, that is n square max alpha square divided by mod of w naught square, which is equal to neta max to beta. And solving for this n max for a given solution vector w0, we find that in maximum n number of iterations can be given as beta mod of w naught square divided by alpha square. That is for if you consider neta is equal to neta n is equal to 1 for all n and w naught equals to 0, then a given solution vector x, and then we have a given solution vector w naught exists, and the rule for adapting the synaptic weight of the perceptron must terminate after n max iteration. That after n max iteration, this iteration is going to terminate. This is going to terminate, and that there is no unique solution for w naught or neta max. Now, considering the above all those discussions that we have, we can state the fixed increment convergence theorem for perceptron as per Rosenblatt, as per Rosenblatt in 1962. That we can state that let the subset of training vector h1 and h2 be linearly separable. Let the inputs presented to the perceptron to the perceptron from these two subset, then the perceptron converges after n0, after in n0 iteration, in a sense that then the perceptron converges in the sense Wn0, okay, is equals to W naught, sorry, W n0 plus 1, W n0 plus 2, and this goes on continuous, and is a solution vector for eta 0 less than eta. Now this is the Roselmann's fixed increment convergence theorem. Okay. Now let us consider next is the absolute error correction procedure. In this step, we'll consider absolute error correction procedure. Now, in the absolute error correction procedure for the adaptation of a single layer perceptron, for which neta n is a variable, now we are considering neta n is a variable, is a variable. In particular, let neta n is equals to the smallest integer for which the condition holds, that is neta n x transpose n xn is greater than mod of W transpose n xn. Okay, this condition must hold. With this procedure, we find that if the inner product of W transpose n xn at the iteration n has an incorrect sign, then W transpose n plus 1 and xn at iteration n plus 1 would have the correct sign. This suggests that if we have W transpose n xn has an incorrect sign at iteration n, we may modify the trading sequence at iteration n plus 1 by setting n plus 1 equal to xn. In otherwise, each pattern is presented repeatedly to the perceptron until the pattern is classified properly. So until the pattern is classified properly, we will continuously go for the iteration. Okay, we'll continuously go for the equation. We'll continuously go for the iteration until the perceptron is classified correctly. Note also that use of an initial vector W naught is different for the null condition, may result in the decrease or increase in the number of iterations required to converge, depending on how W naught 0 relates to the condition W naught. Regardless, the value assigned to the W naught, the perceptron is assumed to be assured of convergence. Now, for if we consider the summary of this perceptron convergence algorithm, we can say that then if we consider a signum function if we consider a signal function of this form is gn of a signal function of form is gn of the form v is equals to plus 1 minus 1 if plus 1 minus 1 or the plus 1 and minus 1 plus 1 if v is greater than 0 and if v is less than 0 we have this function, and we may thus express the quantized response yn of the perceptron in a compact form as yn of the output in a compact form as signum of w transpose n xn xn, and if you notice that input vector xn is a m plus 1 vector whose first element is a fixed at plus 1 throughout the computation, and corresponding the weight vector wn in an m plus 1 by 1 vector whose the first element equals to the bias. One other important point to note that if we have introduced a quantized desired response dn, this is a quantized desired response, that is dn will be, if dn will be is a if our desired response of dn will have plus 1 and minus 1 belongs to if plus 1 if xn belongs to class c1 if xn belongs to class c2. Thus, the adaptation of the weight vector wn is summed up by nicely in the form of an error correction rule, which can be written as wn plus 1. This is for the error correction rule we are discussing. Wn plus neta, the desired response, minus the actual response into xn. Okay, and this is the learning rate parameter. And the difference, this difference plays an important role of error signal, and the learning rate parameter is a positive constant limited to a range of 0 less than equal to neta less than equal to 1. When we assign a value to it in this range, we must keep two things in our mind. First, averaging of past input to provide stable weight, which requires a small neta 1, and for the first adaptation with respect to the real changes in the underlying distribution of the process responsible for the generation of input vector x, which requires large, and this is the first condition and this is the second condition. Okay, so in today's session we have learned about Perceptron Convergence theorem, and we have proved in the Perceptron Convergence theorem we have proved two rules. One is for the fixed increment adaptation rule. Second, we have fixed increment convergence theorem, and second, error correction procedure for the adaptation of a single layer perceptron. Thank you all. Thank you for the today's session.